Hello my dear PUC champions, welcome to Deeksha Karnataka YouTube channel, and in the Masterstroke series today I am going to discuss the last chapter, that is semiconductors. So if you are someone who is looking for revision of the chapters, entire in-depth concept clarification both for your PUC as well as your KCET exam, then Masterstroke series, here we are discussing each and every chapter. We have already completed 13 physics chapters and semiconductor is the last chapter, and if you want to download the PDF of each and every lecture, then definitely you have to join the WhatsApp channel. The link is given in the description section of this video. And also, if you are someone who have not yet subscribed, don't forget to subscribe. Subscriptions are important for us so that we can grow and we can bring more such content for you. Now let us continue. Before I start, just wanted to tell you what are the concepts that we are going to discuss in today's lecture. So we will discuss semiconductors and band theory. We will discuss classification of semiconductors, P and N type semiconductors, PN junction diode, biasing of diode, and obviously application, that is half wave and full wave rectifier. Okay, so let's start. Before I start, I just wanted to recall one concept from your current electricity chapter, which is the conductivity. Different substances have different conductivity. What are the substances that we are talking about? In terms of conductivity, you can classify substances into three broad categories. One is metals or conductors. Okay, they possess very low resistivity and very high conductivity. Remember that. So in terms of conductivity or sigma, okay, this is the symbol sigma, the conductivity is very high. So if you are given some values and they ask you identify which of them is conductor, you need to realize that the conductor will be someone which has a high conductivity as well as very low resistivity. Okay, once in KCET there is a question came, I think 2025, the unit they have changed into ohm centimeter, but don't worry about the unit as of now. Only thing that you should be worried about if the value is very high or very low. Okay, if they are asking you about conductivity, conductivity should be very high for metals or conductors, okay, and resistivity will be very low. So this is how you should remember. Very low means 10 to the power value will be negative for resistivity, 10 to the power value will be positive for conductivity. Insulators are exactly opposite to that of conductors. Okay, insulators have very high resistivity and very low conductivity. Okay, so their conductivity will be in the negative value and their resistivity will be in the positive value. Okay, that is the basic that you should remember at all cost. Second, the third and the not the least, last but not the least, is semiconductor. Semiconductors are somewhere between conductors and insulators. So they will start from some negative value. In both cases, they will start from some negative value, they will go towards some positive value. Okay, so if you see that resistivity goes from negative 10 to the power of minus 5 to positive 10 to the power of 6, and conductivity goes from 10 to the power of 5 to 10 to the power of minus 6. So resistivity and conductivity both have positive and negative values in their 10 to the powers. Okay, so this is the easiest one, right? Semiconductors, if you see that no matter conductivity or resistivity is being asked, you have to see that okay, if one is positive, one is negative, then that will be semiconductor. If conductors generally have high conductivity, conductor, that is the name, that's why they are called conductors, and low resistivity. Insulators, they are exactly opposite to that of the conductors. That's how you can remember these values. You don't need to mug up these values. If you understand what is the meaning of conductor, insulator and semiconductors, you can answer if there is a MCQ question based on this concept. Now let's move on with band theory. Inside the crystal means each atom, when they are kept in certain conditions, they form a specific structure. That structure is called crystals. Okay, for example, one of the common crystal structure is our sodium chloride. Okay, sodium chloride forms a hexagonal crystal structure. Similarly, all the metals also, they generally form a crystalline structure. All for example, our semiconductors also form crystalline structure. Crystalline structure is basically a macroscopic view of the element. Okay, it is not the atomic view, it's a macroscopic view where many atoms are together, they are staying together inside a certain space. Okay, so inside a crystal something incredible happens is that each electron has unique position. So when we talk about atoms, generally we say that all electrons have same energy, electrons are almost moving at the same position. But when you are talking about crystalline structure, there will be a temperature difference between one point and another point, okay, one atom and another atom. Okay, so what happens in that case is that each electron placed in a conductor or insulator or semiconductor, whatever you are considering, each electron's energy is not same. Okay, each electron have different energies, even though they are orbiting in the, say, outermost orbit. Okay, that is the valence shell. So even if all the electrons are located in the valence shell, okay, they all have different energies, right? Now in this portion we are not going to discuss anything below valence shell, so we will target valence shell and the next shell, which is empty by normally, which is empty by chemistry standards. Okay, so those two orbits are our main important orbits. Okay, so when I am saying that there is orbit means you have to understand valence shell, and if I say conduction orbit, that is the outside the valence shell. So we know that chemical property are restricted to valence shell. All the electrons taking part in chemical reactions, they has to be in the valence shell. But in electricity chapter, okay, if electrons are free, we have mentioned that metals have a lot of free electrons. What is the meaning of that? Free electrons means electrons are not restricted to valence shell. They have moved out of valence shell and they are in the next orbit, which is called conduction orbit. If electrons are there in the next shell or next orbit of valence shell, then electrons are considered free. They can take part in the conductivity process. Okay, so these are the basics of band theory. So now, as I mentioned, that each electron in the valence shell, they all have different energies. Now it is very difficult for us to study all these single individual electrons if we cannot put them in a single area, single region. Okay, that is why what we do is that these different energy levels will with continuous energy variation from what we are called energy band. So now in this chapter and in conduction, whenever we are talking about conduction, we are not specifically talking about orbits, we are talking about band. Band means is basically, orbit is, you can consider like a single rubber band, okay, that is you are using to tie something up. And band means the friendship band that you wear during your friendship day, or maybe some of you have given during your special ones during some special day, right? So that shape is band, right? So single rubber band is orbit, and that flat shaped similar thing is a band. Okay, almost of the same material. Okay, only the thing that is little bit thicker, little broader as well. So that is called a band. So band means when multiple, you can consider that if you put up multiple rubber bands together, they give you that kind of friendship band, right? So band means variation of energy. All the variations are listed one by another and they are forming a continuous zone of certain energy. Okay, the energy band, which includes the energy levels of the valence electrons, is called valence band. Okay, valence band, now from now on we will no longer talk about valence orbit, valence shell. We will only talk about valence band. Valence band means all the electrons of all the atoms, okay, inside a crystal, they are present in that zone. Okay, whatever energy you talk about, they are all present in that zone. That is the valence band. Okay, the energy band above the valence band is called conduction band. Okay, conduction band, if the electron moves from valence band to conduction band, they are free to move and they can conduct electricity. Okay, the gap between top of the valence band and bottom of the conduction band is called the energy band gap or energy gap EG. For forbidden energy gap, it may be large, small or zero depending upon the material. So as I mentioned, so for example, I am taking one element. Okay, suppose I am taking one element, all the electrons, suppose this is electron number 1, electron number 2, electron number 3, okay, electron number 4. These are the all energies of the valence electrons present in a material. Okay, so when you are considering, okay, this all the electrons whatever present, there are 1000 numbers of electrons, right? Okay, innumerable, almost Avogadro numbers equivalent electron in a 1 mole of element, right? So those electrons, they all have slightly variation of energies, okay, based on their temperatures, based on their positions inside the crystal. Okay, they will vibrate differently and they will have different energies. So this is valence band. Okay, so this is the energy gap of all the electrons present inside it. Now the next empty band, here generally no electrons are there, but if the electrons are there, there will be also some energy gaps, okay, because energy required to jump from this to this will be varying for individual electrons, right? And based on that also the energy gap will be varied. Suppose electron is there, so each and every electron will have a different energy level, and this is called conduction band. If somehow electron is able to move from this position to this position, then we will say the electron is free, and we will say that this electron can conduct electricity, right? The energy gap means, suppose the energy gap is basically the top of the valence band and bottom of the conduction band. This is called energy gap. Okay, this is called energy gap, and it is denoted by Eg. This is called energy gap, sometimes forbidden energy gap. Okay, forbidden energy gap means electrons are not allowed, generally electrons are not allowed to leave valence band and go to conduction band. That's why it is called forbidden energy gap. But obviously many things are forbidden for you, but you still do it, right? Similarly, electrons are also like you, they don't want to be confined inside this room. So now your exam is going on and your parents are saying, no, you are not allowed to play Free Fire, but you still managing some time to play Free Fire, right? So that is a forbidden task for you, but you are still doing it. Similarly, electrons are also saying, even though it's forbidden, but I want to check what is there. So that's why it is called forbidden energy gap. Now we have to discuss three different cases. Case number one is conduction and valence band overlap. So what happens in this case? If you see that this is the valence band EV and this is the conduction band, okay, and if you plot this graph, you will see that the conduction band and the valence band, they are actually having a zone where they are overlapping. They are having a zone where they are overlapping. Okay, this is called, this is the property of metals. So in this case there is no energy gap. So no energy gap means energy difference or forbidden energy gap is zero. So electrons can freely move from valence band to conduction band. Okay, so when there is no exam, you are allowed to play Free Fire, you are allowed to play cricket, you can go anywhere you want, okay, within that limited space, right? Not outside of your city or without the parents' permission, but without parents' permission also you are allowed to go play cricket, you are allowed to play Free Fire once your exams are over, right? Similarly, so you can consider this is that phase. Okay, so in that phase you can go anywhere within your city limits. You can go you can play some match against some rivals, right? So this is the case of conductors. Conductors are after exam state. Okay, so the resistance of such materials is very low and conductivity is high. Such materials are called conductors. So this is the definition of conductors in terms of band theory. So there is a popular question which sometimes may be asked, that in terms of band theory, differentiate between conductors, insulators and semiconductors. So you have to mention that in case of conductors, first of all, conduction band and valence band overlaps and the energy band gap is zero. So electron can easily move from valence band to conduction band and conduct electricity. They have low resistance, high conductivity, and they are metals or conductors. Now if the energy band gap is greater than 3 electron volt, okay, the band gap is considered to be large. So if the energy band gap is greater than 3 electron volt, the band gap is considered large, and those kind of type of materials are called insulators. Okay, there are no electrons in the conduction band and therefore no electric conduction is possible. Okay, this is the case of insulators. So insulators having a very large band gap, electrons are not allowed to leave even so this is the exam phase. Okay, when our exams are going on, you are not allowed to go outside, you have to stay inside, you have to study for long hours, right? At least in your parents' eyes. So these are the exam phase, this is the case of large band gap insulators. Next is finite but small band gap. So this is like your midterm exam phase, okay, midterm or unit 1 exam phase. So when you are still can go out if you at least study for 4-5 hours. So your parents will say, okay, you go to your college, come back, play for one or 2 hours, then you have to study for 5-6 hours, but no free fire for you. Okay, so this is the stage where band gap is small, less than 3 electron volt, but still it is not 0. Okay, because of the small band gap at room temperature, some electrons from valence band can acquire enough energy to cross the energy gap and enter the conduction band. So at room temperature, some electrons are allowed to move from here to here based on the kinetic energy of those electrons. Okay, these electrons, though small in numbers, can move in the conduction band. Hence, resistance of semiconductors is not as high as that of the insulators. Okay, so electrons can move from valence band to conduction band subjected to some condition that obviously not all electrons are allowed, some of the electrons are allowed, and if the temperature increases, the band gap decreases. So as the temperature increases, band gap decreases and electrons are slowly can move out of the band. Okay, now so if you are in that zone where you are preparing for your board and KCET and you are still stuck between valence band of board exam and you want to cross over to the KCET conduction band, then definitely KC30 batch is here, where we will help you to achieve the crossover of will give you the required forbidden energy gap so that you can cross the valence band to conduction band. Okay, so this crossover is not very simple, as you have learned. So basically you are like a semiconductor right now, where you are thinking, you are trying to make some sense that I want to move from valence band to conduction band, and you are confused what to do. Then KC30 batch is ideal for all of you, where you will get 30-day online live crash course. Then you will get KCET previous year questions with solution. Video lectures is there, complete syllabus revision through video lectures 1 and 2, PU1 and PU2 both will be covered. Chapter wise KCET PYQs in the test format. So quiz, PYQ quiz is available in KC30 batch as well as you will get 10 full length KCET mock test papers, right here, and everything is priced only for 2499. It's a complete course. So if you want to cross the C from valence band to conduction band, then definitely this much is the energy band gap price that you have to pay, right? This is the EG, you can say this is the EG for this course. Okay, so if you pay this much, you will be able to cross the C, right? And the price is only valid till 25th of February. After 25th of February, the prices will go up. So don't wait. Even though the classes will start from 21st of March, you might be thinking I will take it up after my board exams are over. But this special price will no longer be available. It will go up. So make sure you take this offer before it runs out. Now, let's move on to the discussion. Now, the third type of conductors are called semiconductors, and semiconductors are basically mainly two types. Elemental semiconductors. Okay, elemental semiconductors are called, examples are silicon and germanium. Mainly these two are the elemental semiconductor. They are semiconductor by element. Okay, and compound semiconductors. Compound semiconductors are inorganic, organic polynomials. Now the examples are not super important, but you should, I believe you should know that, because organic polymers based semiconductors are used in our mobile phone displays, TV displays. The mobile phone from where you are watching maybe either OLED or AMOLED. Most of them are AMOLED. So AMOLED, even the TFT displays or older generation displays, they are also based on organic semiconductors. And because of the semiconductor process is possible, we are able to communicate via video calls. We are able to see each other in video messages, right? The computer system, the mobile system, everything is based on displays, and that display is basically based on semiconductors. Clear? most of you are wondering what is OLED, organic light emitting diode. Organic light emitting diode. Diode is obviously based on semiconductor. It is based on organic light emitting diode. So it is also a type of semiconductor. AMOLED is also a type of OLED. Okay. Now let us move on to the second type of semiconductors. So semiconductors can be classified based into, one is whether they are element or they are compound. Second is how they are being produced. So one is intrinsic semiconductor and extrinsic semiconductor. Obviously the elemental semiconductors are called intrinsic semiconductors. Compound based semiconductors, doped versions of semiconductors, they are all considered to be extrinsic semiconductor. Okay. Now what is intrinsic semiconductor? Intrinsic semiconductors are naturally occurring elemental semiconductors are called intrinsic semiconductor. There are only two types of intrinsic semiconductor, germanium and silicon. GE stands for germanium, SI stands for silicon. The crystal structure, also called lattice structure. Lattice structure is the name that is given to the crystal structure. As I mentioned, that all the atomic atoms, when they are individual, they are called atoms, but when they are sitting together in a party hall, then it is called a gathering or a function. Similarly, it is called crystals. Okay. So when you are alone at home studying, it is simply you, but when you visit some friend's place, you are having some party, it is called a gathering. Right, so it is basically gathering of all the atoms. Now based on the atoms and element, the structure of the gathering can be different. Okay, so here silicon is a tetravalent structure. So what it does, it has a valency 4 and its external most extreme shell, that is valence orbit, it has 4 extra electrons. Okay, 4 extra electrons means it can either take 4 electrons or it can give 4 electrons. But as we know, similar for carbon as well, it is very difficult to take 4 electrons or give all 4 electrons. So what it does, it makes covalent bonds. Covalent bonds are much easier to form. So what is a covalent bond? Covalent bond is when they share these electrons. Okay, instead of completely giving it to someone else, what they say that, okay, you give 1 electron, I will give you 1 electron, we will share 1 electron each, and that's how we will form covalent bonds. So that's why each silicon is covered by other 4 silicons. So this silicon is covered by this one, this one, this one and this one. Okay, so as you can see, this silicon is connected to this one and this one. So there are 4 covalent bonds for each silicon. Okay, and each of them is giving sharing one electron. So the closer electron is for this. So as you can see, this electron is given by this element, this is given by this element, and so far and so on. Okay, so this is how the electrons are shared. So and once they are all shared, then every silicon has 8 electrons and they are all happy and satisfied. Okay, we all have 8 electrons in our outermost orbit. That is the stable number for all elements. Either 2 for hydrogen and helium, and then otherwise it is always 8, right? The crystal structure, also called lattice structure of silicon and germanium, are shown over here. We know that silicon and germanium have 4 valence electrons. Every silicon or germanium atom share one of its 4 valence electrons with each of its 4 nearest neighboring atoms. These shared electrons pairs are referred to as forming a covalent bond or simply a valence bond. Okay, so this is valence bond or covalent bond. That's how they are stable. This is the intrinsic semiconductors. Okay, now let us discuss one more important concept, which is holes. What is a hole? Okay, some people think it's a positively charged particle. Some people think that it is just basically something which carries positive charge. Actually it is not. What is a hole? So thermally excited electrons leaves the bond and creates a vacancy with an effective charge of plus Q. Actually not only plus Q, it will be plus E. E is the charge of an electron, right? So you can say this is plus E. Now, what is the meaning of that? So we know that when you increase the temperature of some metal or element or some material, what happens? The electron starts vibrating. We have understand that, right? So when you are increasing the temperature, what is the basically meaning of increase of temperature? Increase of temperature means atoms are vibrating, the electrons are vibrating, everything inside the crystal structure, everyone is vibrating. and during that vibration what happens is that some of the electrons can exit this covalent bond if they gain sufficient energy. One of these electrons will be loosely bound. On those loosely bound electron will say, no, I will not stay in my parents' place, I want to go out, I want to be a rebel, okay, I want to play even during exam, I want to play free fire even during exam, I don't care whether my mother beats me or my father scolds me, I will play the game. So there are few electrons like that as well. Okay, so what happens, these electrons come out of the bond. Okay, once they are out of the bond, what they will leave a hole inside their places, because everyone is electrically neutral, and to sustain the bond there was one electron shared by this, one electron shared by this, but because this electron has left this site, okay, there will be a vacancy. Okay, so hole basically is a vacancy which is left by a electron which is moved out of the bond. So hole is nothing new, it is a vacancy which is created by outgoing electron. Okay, this vacancy with the effective positive electronic charge is called a hole. Okay, so there are a few instances where they ask what is a hole. Hole is not a positively charged electron or positron or a positively charged proton. It is basically a vacancy created by electron who left the bond. The hole behaves as an apparent free particle with effective positive charge. So now once this hole is being created, what it will do, it will try to attract some electrons from other bonds. Okay, it will try to attract, I am positive, you are negative, come towards me. Okay, and once this electron moves, then what happens, there is another hole is created. So this hole, what it will do, it will try to attract this electron. Okay, this hole will try to attract this electron, and once this electron moves out, here another hole will be created. This hole will attract another electron, and there will be another hole will be created. So basically, because electrons are moving in this side, we can say that hole is actually moving in the opposite side. So hole can move like a free particle because it can be influenced by external electric field, by external temperatures, and it can attract other electrons, and it can move from one place to another. Okay, in intrinsic semiconductors, the number of holes and number of free electrons are equal. Okay, obviously, because there is nothing else. So if one electron left the bond, then there will be one hole will be created. If 10 electrons leave the bond, 10 holes will be created. So holes and electron number are same for intrinsic semiconductors. That is, Ne equals to Nh equals to Ni, where Ni is called the intrinsic carrier concentration. Generally, if there is a numerical question comes from this concept, they will give you intrinsic carrier concentration. They will not give you anything else. So intrinsic carrier concentration itself is the hole concentration, itself is the electron concentration. The total current I thus is the sum of the hole current plus electron current. So I is equal to IE plus IH. Okay, that's just for concept. Next, move on to the next part. Extrinsic semiconductor. Now, intrinsic semiconductors are tricky to use because pure silicon, pure germanium, they are first of all, only way you can make them a conductor by heating it up, okay, or increasing its temperature. Then only more and more electrons will be free, and more electrons free means more number of holes are created. Again, you cannot control number of holes and number of electrons, so either it will be creating same number of holes as electrons. So conductivity management is very, very tricky. Okay, so what people have thought, okay, we cannot put every time when we want to use a mobile phone, we cannot put it inside a electric heater or inside a fire, right? Even though the concept came before discovering a mobile phone, but just imagine that suppose you are using a mobile phone, every time you want to use it, you have to put it inside a microwave or some oven or some gas fire. Okay, you have to put on the fire, then you use put on the mobile phone in the pan, then only it works. That is very, very tricky and disgusting, right? Your phone will burn, then it will be useful. So what is the idea? How can we overcome this? So that's how the people came up with an idea of extrinsic semiconductor. Okay, the conductivity of an intrinsic semiconductor depends on its temperature, but at room temperature the conductivity is very, very low. Okay, as such, no important electronic devices can be developed using these semiconductors, right? Now, Hence, there is a necessity of improving their conductivity, and to do that, we have to use some impurities. Okay, we have to add some impurities so that their conductivity increases. Right? So, how to do that impurity? So, we will do a small amount, say a few parts per million. So, 1 million, 1 impurity. Okay, impurity 1 atom per million atoms. So that is the parts per million, ppm. It is a measurement that you have studied in chemistry, right? So 1 atom per 1 million is 1 ppm. Okay, so maybe 10 ppm, maybe 20 ppm, but not more than that. So few parts per million, few parts means 10, 20 per million. So 1 million original atom, we are adding impurity of 10 atoms. Okay, of a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor is increased many-fold. Okay, so conductivity increased many times, and that is the use of this extrinsic semiconductor. This is the basic of extrinsic semiconductor. Okay, such materials are known as extrinsic semiconductors or impure semiconductors. So if sometimes we say that pure thing is good for our everything, but at times pure is not that good, impure is better. So one example is this semiconductor. Okay, so impure things can be better. Example, obviously semiconductor. Pure semiconductors are almost useless unless you dope it with impurity. The deliberate addition of desirable impurity is called doping. The process is called doping, and by doping what you have done, you have improved its efficiency, you have improved its working. And that's why in sports you may have heard that someone failed in dope test. Okay, doping is a process where you increase someone's efficiency, someone's power by infusing something which is not actually meant to be there. Okay, so if you take some medication, some drugs which you are not supposed to take normally, and if you are taking them, that improves your performance, your capacity, then it is called doping. Same concept goes for semiconductors as well, and semiconductors, when you are improving its performance, it is called doping. Okay, and impurity atoms are called dopants. Such material is also called a doped semiconductor. So extrinsic semiconductors, doped semiconductor, same thing. There are two types of dopants used in doping to tetravalent silicon or germanium. So no matter what you are using, silicon or germanium, you can use same type of dopants. Pentavalent means 5, penta means 5, so valency is 5, like arsenic, antimony, phosphorus, etc. So these are the elements you can dope to make it a special type of semiconductors. And another one is trivalent. So as you can see, the normal valency of silicon is 4, so you can use either one more or one less. You cannot use any other dopants. Okay, trivalent example, indium, boron, aluminum. Now these examples are very common and important because they might ask you, if I want to make such and such type of semiconductor, which dopants I will use. Okay, for number of holes and number of electrons, the equation which is valid for a semiconductor is given by Ne into Nh equals to Ni square. So where Ni is the intrinsic semiconductor concentration, and Ne and Nh is the, when you are doping it, whatever is the electron and hole concentration, this formula should be used. Easy formula. Based on this, might be you will get 1 or 2 numerical question in KCET, maybe 1, not 2. Okay, so let's remember it for future use. Now, N type of semiconductors. So now, as I am mentioning that there are two types of semiconductor you can create using two type of dopants. If you infuse pentavalent material into a trivalent silicon, you will get a N type semiconductor. Okay, this is to obtain when silicon and germanium is doped with a pentavalent impurity like phosphorus, arsenic and antimony. The extra electron in the pentavalent atom can be made free and can participate in conduction. Here the ionization energy required to set this electron free is very small, and even at room temperature it will be free to move. the energy required is almost equal to 0.01 electron volt. So this is the energy gap of we will say this is the energy gap of the donor level and the acceptor level. Okay, donor level and conduction band. Okay, so what is donor level I will explain in a while. Okay, and 0.05 for a doped silicon. For germanium it is smaller, even smaller than silicon. Okay, to separate this electron from this atom. For reference, 0.72 electron volt for germanium and about 1.1 electron volt for silicon when they are pure. So you need a almost fraction, 100 times less than the whatever original energy required to free one electron. Okay, for n-type semiconductors we have number of electrons or electron concentration is much higher than hole concentration. Okay, now let us understand the concept once. What happens is that suppose we have a silicon atom, okay, and it has how many electrons it is sharing? It is sharing with 4 other silicons, right? Now when you dope it with a pentavalent atom, the atom is very much in shape and size almost close to silicon. So what it will do, it will immediately release one extra electron and sit tight with all the silicon. So basically you visited say a party and you see that everyone is wearing a cap. Okay, everyone is wearing India's cap. You don't have any cap. So what you will do, you have 2 caps. Okay, everyone else has only 1 cap. What you will do, you will wear 1 cap and you will throw the other cap away. Okay, so that someone else somewhere can wear this extra cap. You wear the cap and you are saying, okay, I also have 1 cap only. Okay, I don't have 2 caps. So basically that extra cap is an electron. Okay, so when you visited a cricket match, you had somehow you had 2 caps, you wear 1 cap, you throw another cap, so that everyone feels like, okay, you are the same. Okay, so this is the try of phosphorus or any other pentavalent element. It will give away the extra electron and it will stay free. Oh, I am same as silicon, you are my brother, I have get rid of extra electron. Okay, so that's what happened. And when you are considering the band diagram, what happens is that normally in case of a semiconductor, this is the valence band, this is conduction band, right? There was an energy gap less than 3 electron volt. For silicon 1.1, for germanium 0.7. Okay, now what happens, there is a new level created because of this this extra electron added by this phosphorus. These electrons all are residing over here. This is called acceptor level. This is called acceptor, sorry, not acceptor, what I am saying, this is called donor level. Okay, this is called donor level. What happens? The electron present in this donor level, they can easily take that extra 0.01 or 0.05 electron volt energy, and they can easily move to conduction band and they can start conducting the electricity. Okay, this is a way of making extra free electrons available to the structure. Okay, the crystal structure now gains extra ability to have some extra electron in the conduction band, and these electrons starts conducting. Okay, so this is the way of making sure that the conductivity of the semiconductor increases. Okay, so how to make a semiconductor n-type? By doping pentavalent element. Next, let's see one question. What should be the density of donor atoms which should be doped with the pure germanium semiconductor in order to obtain an n-type semiconductor whose conductivity is 5 mho per centimeter? Mobility of electron in n-type germanium is 3900 centimeter square per volt per second, and density of holes is negligible. Okay, so we want to make a conductor of this much conductivity. Okay, and they ask you what is the amount of what should I say, dopant is required. Okay, so conductivity is given 5 mho per centimeter. Mho means This is the symbol for mho per centimeter, and the mobility of electrons is given by 3900 centimeter square V square second. You can ignore the holes. Holes you can ignore. Now you have to calculate the number density that is required for this electron to be free. This much this much conductivity to gain. Now we know that conductivity is given by, normally conductivity is N charge of an electron into mobility, and in general it is basically if you have holes and electrons both, so here you have to add a number of electrons density and plus number of hole density, and hole and electron generally have different types of mobility, so based on that you may have to adjust this number. But because it is KCET, because it's Comet K, this question came in Comet K, by the way. So if you are appearing for such exams, they will not give you complicated questions, and the questions will be simple. So as you can see, you can ignore the number density of your holes. So number density of holes are ignored. So only electron density, that is Ne, it is given by sigma divided by E into mu. Do not ignore this mu. From unit calculation you might think that okay, it will be the sigma by mu anyway, but there is also an electron involved, so that's why the value is starting from this high value. Okay, so sigma is given by 5 and mu is given by 3900, and 1.6 into 10 to the power of minus 19 into 3900. Okay, now let's try to simplify this. You will get this as approximately 5 by 6. Okay, approximately 5 by 6, and it will be 1 to 3 10 to the power of 16. 5 by 6 into 10 to the power of 16. Okay, approximately, and that will be approximately 0.8 or 8 into 10 to the power of 15, approximately 8 into 10 to the power of 15. So correct answer is this one. Okay, you can check this out, multiplication and approximation. So if you are someone who is practicing more and more, there will be no trouble for you to finding 1.6 into 3.9. Okay, so that's one, that type of calculation comes with practice. I don't request you to practice it now, but we will be practicing more such calculations and tricks during our after board exams. Okay, now let's move on to p-type semiconductor. This is obtained when silicon and germanium is doped with a trivalent impurity like aluminium, boron, indium, etc. Examples are important, by the way. The dopant has one valence electron less than silicon and germanium, and therefore this atom can form a covalent bonds with neighboring 3 silicon atoms but does not have any electron to offer to the 4th silicon atom. So the bond between the 4th neighbor and the trivalent atom has a vacancy or hole. For p-type semiconductor, obviously number of holes concentration is more than number of electrons. Now let us understand this. So we have our central of attraction silicon. It is making 4 bonds with some other silicons present nearby. Okay, all of them are silicons. Now you doped it with some element, say boron. Okay, boron is one name, that's why I'm using it. So you can use aluminium and indium as well. So boron, what it is doing, it has only 3 electrons, so it is forming only one bond, okay, on all sides, but it has 1 electron less. What happens to that? So that extra electron, what it will do, it will fetch that extra electron from some other bond. It will make a clean and clear bond, but there will be 1 extra electron gone from the next silicon. Okay, so this silicon will try to fetch another electron from some other bonds. So what will happen, there will be always a motion of a positively charged particle, and that particle is obviously vacancy, and that vacancy is like a hole. So I am giving one example in the same cricket match where the phosphorus throwed away the extra cap. Now imagine the same match in the other side of the stadium where someone entered the stadium and he saw that everyone is wearing a cap, but he does not have a cap. So what he will do, he will look left and right, he will take one cap from someone, wear it, and he will say, I have a cap, I don't know. Okay, so the person who loses his cap, what he will do? He will say, Arey, my cap is gone, I have to take some from someone else. So he will take from someone else, and like that one people will go out of cap as well. So this is the P type of semiconductor. P type semiconductor, there is a vacancy or extra hole is created through this method. Okay, so this is the method where you are using creating extra holes. In N type you are creating extra electrons, in P type you are creating extra holes. Now what happens in this case is that, so this is conduction band, this is valence band, and what happens, it is the acceptor level, and in this level what it does, it takes away electrons from the valence band, and once the electrons are being moved out of the valence band, okay, it leaves out a hole. So remember that holes are always located in the valence band, free electrons are always located in the conduction band. Holes are always located in the valence band, free electrons are always located in the conduction band. Okay, in general number of holes in the conduction band are not there, because conduction band, by starting with, they are free of electrons, so any electron moving to conduction band are coming from valence band itself. So except for metals behave slightly differently. For semiconductors, all the holes are located in the valence band, all the free electrons either they are located in the acceptor level or in the conduction band. Okay, not all the electrons, valence band do consist of electrons as well, but holes are primarily located in the valence band. Okay, now acceptor level is basically the level where electrons are being taken. Normally if you want to transport an electron from valence band to conduction band, it requires a lot of energy, but transfer an electron from here to this newly created level, which is called acceptor level, is very less amount of energy, and that's how this conductor behaves like a positively charged holes. Okay, in an N-type semiconductor, the concentration of electron is more compared to holes. Similarly, in a P-type semiconductor, the concentration of holes is more than that of electrons. Due to the concentration difference across P side and N side, during PN junction formation, holes diffuse from P side to N side and electrons diffuse from N side to P side. With this motion of charge carriers gives rise to a diffusion current across the junction. Okay, so let us understand this. Okay, so let us understand this. I will go back to there later on. So first, P and N are created separately. Now if you try to create a crystal where one side of the crystal is doped with trivalent and another side is doped with pentavalent, then we get a unique combination which is called PN junction. Okay, now remember, you cannot create a PN junction by taking a P type and N type and merging them separately. You have to form PN junction by doping a single crystal simultaneously from one side P, another side N. Okay, there are sophisticated machines, sophisticated technology. Through that you can obviously do it. Obviously at size of the diode is of the microns. Now obviously that is something we have achieved. And even nanometer diodes are also possible, so smaller diodes are also possible using sophisticated mechanism. Okay, and all these cases you are not joining two diodes separately, you are creating this design by fabricating in a single piece of crystal. Single piece of crystal means this is a silicon wafer. Wafer means the same piece that you use for your fun, so that kind of things are called silicon wafers. So those wafer are being taken, they are put in a vacuum chamber. one side is doped with say positively charged, not positively charged, trivalent aluminium, one side is doped with pentavalent phosphorus, and you get this kind of structure. Now once this structure is formed, what happens? The electrons present in the n side, they start to move in the opposite side where there are extra holes. Similarly, holes will move from p side to n side. Electrons will move from n side to p side. Holes will move from positive side to negative side. P and n basically means positive and negative. P for positive, n for negative by default. Now what happens? The crystal was originally neutral. So that means the entire positive and negative was balanced in case of n side. Entire positive and negative was still balanced for p type. So there is a trick question. What is the total charge of a p type semiconductor? Total charge of a p type semiconductor is 0. Even though we have extra holes, total charge is still 0 because electrons are not created or not destroyed. Okay, so total charge of, because we are only using elements, okay, ions are created by this process, but electrons and protons in the same way are not being created or destroyed. That means you are not creating any extra charge. Okay, you are only make sure that electrons are free to move. That's what you are only doing. Electrons or holes, whatever in this case, they are free to move. That is the process is doing. So they are not creating any extra charges or not adding any extra charges. That's why p type and n type are always neutral in nature. Now a neutral object, it is slowly started gaining electrons. A neutral object in this side, they are slowly started gaining holes. So what will happen is that there will be a potential barrier will be created. This is very, very important to understand. The neutral side will gain positive charge. So what will happen, even though it has extra electrons, once it has gained enough positive charge, it will stop remaining electrons to move to the other side. Okay, because electron wala side is now positive and the positive wala side is now negative. Okay, so they will try to stop the mixing anymore, and they will say, okay, we will, whatever fighting was going on, the fighting is over. And this center, at the center of p and n, there will be a region where all the dead soldiers are lying like this. So positive and negative are two enemies. They fought for some time and some of them are died. So this is the region where no active participation is there, and this region is called depletion region. Depletion means it is depleted of all the active charge carriers. That's why it is called depletion region. Okay, now let's go back to our previous case. So this is the diffusion. Diffusion means electrons are going from n to p side, and positively charged holes are going from p side to n side. When an electron diffuses from n to p, it leaves behind an ionized donor on n side. This ionized donor or positive charge is immobile as it is balanced to the surrounding. Okay, now what happens is that as the electrons continue to diffuse, so even after the electrons are going out, the positively charged donor atom are still left inside in the n side. What happens is that a layer of positive charge on the n side junction is developed. Similarly, the holes diffuses to the opposite side, and a layer of negative charge layer of the p side junction is developed. Okay, so this side becomes positive, this side becomes negative. Okay, this space charge region on the either side of the junction together is known as depletion region. So there is no charge, all charges have depleted, all of them have died. As the electrons and holes taking part in the initial movement across the junction, depleted region of its free charges. Okay, the potential difference developed is called barrier potential, and it stops any further mixing of charges. So this is a barrier potential. What happens when the charges are mixed? Some soldiers have died, then they said, okay, ceasefire, there is no longer fight, and you get a barrier potential. Okay, so this side is negative, this side is positive, and the current or initial current stops. The thickness of the depletion region is on the order of 0.1 micrometer. Okay, for a general diode, the depletion region width is 0.1 micrometer. An electric field is directed from N side towards the P side. Now this is for typical diodes. Obviously, as I mentioned, there are different types of diodes. The depletion width can vary, but for a typical silicon based diodes, the width of the depletion region is 0.1 micrometer. Okay, as the electric field directed from N side towards P side, due to this field, electrons on P side of the junction moves to the N side and hole on the N side of the junction moves to the P side. The motion of charge carriers due to this electric field is called drift current. So what happens is that electrons, because there is an electric field directed in this side, positive to negative, so this side becomes now positive, this side is now negative. So there is a electric field in this direction, right? Positive to negative, electric field is always directed from positive to negative, and because of this electric field, electrons present in the P side, they start drifting in this particular direction. Okay, electrons present in N side, they diffuse. If you remember, electrons diffuse from N to P side, but they drift from P to N side. So whatever electron is diffusing from N to P, the same amount of electron are now coming back. So there is a time up to which the equilibrium is established. When the equilibrium is established, the diffusion current and drift current, they are equal. Okay, due to this field, electrons on the P side of the junction moves to the N side and hole on the N side junction moves to the P side. The motion of charge carriers due to this electric field is called drift current. In a PN junction under equilibrium, there is no net current, that is diffusion current and drift current are equal. Okay, if it is not connected in a battery or when you are not using it, the drift current and diffusion current are exactly equal and opposite. So basically it stays neutral. Now again, one more important point, P type, N type, PN junction, all of them are electrically neutral when there is no current flowing through it, no external electric field is applied. Okay, a semiconductor diode is basically a PN junction with the metallic contacts provided at the ends for the application of voltage. So if you take a PN junction, you add some metal contact and you allow some current to pass through it, then it is called a PN junction diode. And this is the actual PN junction and this is the symbol of PN junction. Okay, remember the arrow points the direction of current. This line represents if the current tries to pass from the opposite direction, it stops it. Okay, the arrow represent if you apply a certain current such that the current is allowed to pass from this side to this side, current is being allowed. If you try to flow some current from this side to this side, current will not flow. Okay, so this is called, we will discuss in the forward biasing of the diode, but you should remember that to make a diode conduct, you have to connect positive with the P type and negative with the N type. Okay, so if you connect a battery, positive over here and negative over here, so that the electric field is directed in this direction, you will see a current passing through the diode. If you do it in the opposite side, it will not allow any current to pass through it. That's why it is sometimes called diode valve. Valve is what? We have valves in our heart, those who have studied biology. Okay, so they allow the flow of blood only in a particular direction. Similarly, valves are there in our everywhere in our life. If you observe any water pipes, starting from water pipes and all the liquid fluid related systems, there is a valve. Valve is basically where current is being allowed to flow only in one direction. It stops the flow in the opposite direction. Similarly, diode is an electrical valve which allows the current to flow in only one direction, but it stops in the opposite direction. Okay. Now, when an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side is the negative terminal of the battery, it is said to be forward biased. Forward biased. Forward biased means current is allowed to pass. Okay. Next is a PN junction is under forward bias. The direction of the applied voltage V is opposite to the built-in potential VO. As a result, the depletion layer slowly decreases and the barrier height reduces. The effective barrier height under the forward bias is V minus V naught or V naught minus V. Okay, so as you are slowly increasing the voltage, what happens is that the barrier potential is decreasing because this negative side is compensated by the positive and the positive side is being compensated by the negative. So this region height slowly decreases and the barrier height also decreases. And when the voltage, external voltage increases, when the external voltage exceeds this barrier voltage, you will start seeing a current. Okay, we will discuss that. We will see that. So when you slowly increases the voltage even further, okay, the barrier voltage becomes 0 and it behaves like a normal conductor and current is being allowed to pass through it. So what we started with our journey through a semiconductor, which was actually you require a heat to work it. Now it is working in normal room temperature and it is behaving like a conductor with a special thing that it only allows the current in one direction, it is not allowing the current in the opposite direction. Normally for a simple copper based conductor, it allows current in both direction. Okay, but sometimes we require a specific device which only allows the current in one direction but it stops in the opposite direction. So that is where this PN junction comes into picture. Now let us see one question. Okay, identify the diodes in which it is forward biased in the following set. So remember that if the voltage of P side is greater than N side, okay, then we say that diode is in forward biased. You have to consider the sign of the voltage as well. So let's see this one, first one. So in first one, this side is 0. This side has a 0 voltage. Okay, this side has -5 voltage. This is the symbol of grounding. So grounding means this has 0 voltage, this has -5. So obviously 0 to -5 current will flow. Okay, 0 to -5 current will flow. That means it is a forward biased. 0 is greater than -5. Obviously magnitude wise no, but sign wise yes, 0 is a bigger number than -5. Now let's check this one. So here you have, this is 5 volt, this is 0 volt. Again current can pass from 5 to 0. This is still higher. Okay, this is higher, this is lower. Okay, so current can pass. So this is also forward biased. Now let's check this one. Here the diagram is reversed, so you have to be careful. On P side we have -2. Always start with P side then N side. So this is the arrow side, this is P side, this is N side. Okay, P side has -2, N side has -7. -2 is bigger than -7. So again current is being allowed to pass, and current is being allowed to pass means this is forward bias. Now let's see the last one. Here we have, this one is 2 volt, this one is 3 volt. 2 volt is smaller than 3 volt. So current will try to flow in this direction, which will be blocked, right? Higher voltage to lower voltage, current always flows from higher to lower voltage. So current will try to flow in this direction, but here we have a barrier, so current will stop. So this is the reversed bias. So 1, 2 and 3 are forward biased, but 4 is reversed biased. So let's see the correct answer. 1, 2 and 3. So option C is correct. So you have to be sure, you have to analyze all the diagrams. This kind of questions are common in KCET exams. Now PN junction diode under reverse bias. Now you have completed your forward biasing achievement. Now you want to do something opposite of that. So what is that? That you connect the negative side with positive and positive side with negative. So let's see what happens. So this condition is called reverse biased. When an external voltage V is applied across the diode such that N side is positive and P side is negative, it is said to be reverse biased. So basically this is common definition, but in terms of general definition, the P side is at lower voltage compared to the N side. So N side is higher voltage, P side is lower voltage. Okay, the direction of applied voltage is same as the barrier potential. As a result, the barrier height increases. So this is very important. In which of the following case barrier height increases? Forward, reverse, no bias, okay, none of the above, or all of the above. So barrier height increases only in reverse biased. Okay, and the depletion region widens due to the change in the electric field. The effective barrier height under reverse bias is V plus V naught. So in this case barrier height increases. Now forward bias and reverse bias characteristic, if you draw the graph, of voltage versus current, you will see that the forward bias, when you are increasing the voltage, okay, so this region you will not see any current. This is the barrier height. This is the barrier height. Okay, so up to this point there is no current, and once the barrier height is achieved, the current slowly starts increasing and it goes in a particular way. This is no longer obeying Ohm's law. Okay, this device does not obey Ohm's law. Current can pass a very high value, and if you see that this is in milliamperes and hundreds of milliamperes slowly, only by changing voltage from 0.6 to 0.8. So you can get a very large amount of current by changing a small amount of voltage. Now what will happen if you do the same thing in reverse bias? So reverse bias, ideally there should not be any current. Ideally there should not be any current. Current should be almost zero, and that is true up to certain limit. The current in the reverse bias is in microampere. Okay, so current in the reverse direction is in microampere, but after certain value, very high value, based on different diodes, it can vary, the voltage can vary. After a certain value, it suddenly decrease, the current starts increasing in the reverse bias as well. Okay, not as sharp as forward bias, but still current increases. This is called breakdown. The diode is broken down, right? So when you are trying to resist something, okay, I will not study, I will not study, I will not study, I will not study, but suddenly in the exam hall your parents are pressuring you, your friends are pressuring you, then you said, okay, I will do it. Okay, so basically this is the moment for diode. Even in the reverse bias, it is trying to stop, suddenly all the level are broke down and it says, okay, I will do it. So then this is the breakdown. Okay, so breakdown means when even in the reverse bias also the diode starts conducting. Okay, and this is very specific case, and there are some mechanism involved with it that are not part of your syllabus. If you study physics or even any engineering branches, I hope that this will be part of the course. Okay, now there are two types of rectifiers, half wave and full wave. So in half wave rectifier, what we do, we have only one diagram. All these diagrams are important, by the way. So these diagrams are very, very important, because in your board exam there will be 99% chance either half wave or full wave, one of the rectifiers will going to come. So in the half wave only one diode is used. So what happens is that this is the AC signal, input AC signal we have learned in the AC chapter. This is how the AC signal looks like, sinusoidal graph. So when the voltage is positive, okay, the diode conducts. Okay, that is, the diode is forward bias, it is conducting and it is giving you a current. Now here we are assuming the diodes are ideal. What is the difference between ideal and practical diode? In practical diode, if you see, this is the practical diode graph. Okay, in ideal diode the graph start from here. Okay, the ideal diode graph starts from here. There is no barrier potential. So barrier potential for an ideal diode is 0, and in the reverse bias it is always giving you flat 0 voltage. Okay, so ideal diode are basically, it is only conducting in forward bias, it is not conducting anything in the reverse bias. That is ideal diode, and barrier potential is almost negligible, and when there is a forward bias you will get a forward voltage as well. Okay, so when the diode is forward biased, it is conducting, it is giving you an output through this resistance, you are collecting the output. So current, basically it is giving a current, and to convert current to voltage you have to add a resistor. Okay, so this is the output voltage. When the current in this, you can ignore the primary and secondary, you can only think about this source as well. Primary and secondary is only shown over here to make you understand that the voltage which is being supplied by the power stations are very high. A diode generally operates in 5 volt to 10 volt range. So we are using a step down transformer to reduce the voltage. That's it. That is the main purpose of this primary secondary portion. Okay, this transformer portion, you can simply say that input is coming from a transformer, but if you draw this diagram, that will be better. Okay, major part you have to understand that AC source, which is basically high voltage, and it is giving you a low voltage. So high voltage to low voltage conversion done by transformer, and then unification of the current, or the one directional of the current, is being done by the rectifier, which is a single diode here. Now what happens is that obviously it is conducting in the forward direction, it is not conducting in the reverse condition. Okay, so this is the output. Now as you can see, the diode is working only half time and it is not working in the second half. So we are losing out on the entire energy section. Okay, so even though it is the start, but it is not perfect. We need better. We need much better than this. So what we will be doing? We will move to full wave rectifier. Now one important thing is that in case of half wave rectifier, input and output frequency are same. Input frequency and output frequency are same. Okay. Input frequency and output ripple frequency. Generally when you are calling a frequency for a DC wave, it is not ideal to say them frequency, but ripple frequency. Ripple frequency means the wave sign, okay, that peak value. So ripple frequency is same. In case of full wave rectifier, ripple frequency is double than the input frequency. That is one point that you may need to consider. Now let us understand. So full wave rectifier, what happens is that it is using two diodes. This is the simplest full wave rectifier. There is a one type of full wave rectifier called bridge rectifier, which is slightly advanced than this. There are many other types of full wave rectifiers, but this is one of the very basic full wave rectifiers where we have two diodes connected. This diode conducts during the positive half cycle. This diode conducts during the negative half cycle. Okay, so this is the positive half cycle for diode 1. This is the negative half cycle for the diode 2. So this diode D1 conducts in this zone, the diode D2 conducts in this zone. Okay, and that's how you are getting all the, now if you see, all the waves of the input are now converted. Now you might say, sir, there are two input waves. There are not two input waves because we have a reference point over here which is connected to the ground. When the voltage for A is positive, same voltage is negative for diode 2. That's what it is being shown over here. Okay, because the reference level we have taken from the midpoint. Okay, when the voltage is positive for diode A, the same voltage is negative for diode D2. When this voltage is negative, the same voltage becomes positive for diode D1 because it is taken from the negative. So if this is positive, this is negative. If this is negative, this becomes positive because the reference point is taken from the center. This is a technique of converting positive to negative. That's it. Okay, so both diodes are conducting and you are getting a current. In both cases, you are getting the output current through RL in the same direction. So here the current in the RL travels in the same direction. So in normally AC travels back and forth, top and bottom, but here after this is current is allowed to pass through this combination, the current through the resistance is passing only in one direction, and that is why it is called a rectifier. Rectifier means it converts AC to DC. Rectifier's job is to convert AC to DC. And in case of full wave rectifier, because it is converting the entire wave, it is the ripple frequency is twice that of the input frequency. So on a half wave rectifier, the input frequency is 50 Hz. The ripple in the output is mainly of the frequency. So ripple frequency for half wave rectifier is same as the input frequency. So it will be 50 Hz as well. Okay. Now here is the formula sheet or chapter summary, you might say. So these are the main things. Okay. Metal in conductors, insulators, semiconductors, intrinsic semiconductor, extrinsic semiconductor, and half wave and full wave rectifiers. Okay, so this is the basic chapter summary. Now if you have any more questions, any doubts, please don't forget to mention in the comment section below. I'll be back with more endgame series. Our endgame series is live. I hope you are watching them. There we are discussing your most important questions of entire PU2 exam. So do join us in our endgame lectures and lives. Till then, bye.